there are other problems. Okay? For example, IA has very poor shape sensitivity because autocorrelation tends to smoothen the original function if you check the definition. Okay. As a result, pulses of very different shapes may have similar intensity autocorrelation functions. Okay, so I show you two examples. Okay, one example. This is the the signal pulse shape. Okay, it's not very standard. It has a large main peak and a small side peak, and it's asymmetric. Okay, and what is the corresponding G2 function? Look like this. Okay, it's symmetric, and you have no idea about the original pulse has two peaks, right? It's a single peak autocorrelation function. So experimentally, if you have this result, how could you imagine the corresponding pulse shape looks like this? It's hardly possible, right? So that's the meaning. The shape sensitivity is quite poor. 即使你量到一个很漂亮的 IA 函数呢，不代表你对应的脉冲也很漂亮，很多资讯消失掉了，因为 autocorrelation 的过程就会把这些不 smooth 的东西把它去掉。OK。This slide is also interesting. We consider the intensity autocorrelation functions of CW noise and noise burst. Okay. Let's start with the normal case. If you have a beautiful single pulse, what is your intensity autocorrelation function? It could be like this. Okay. And this is correlation with delta tau. By using the deconvolution factor, you might estimate what is the real pulse width by this measurement, right? Then, what happens if your input signal is not a single beautiful pulse, but continuous wave noise? What is continuous wave noise? Mathematically, it means your temporal envelope function A of t is equal to A sub n of t. N means noise. And it's a complex function. Your real part and the imaginary part are just two Gaussian random variables of zero mean and the standard deviation sigma. So this is totally random, CW noise. Okay. So if your input signal is CW noise, after intensity autocorrelation measurement, what do you get? Okay. You can get something like this. You have a sharp spike, okay, and atop a constant background. Okay. But if you are unaware of the theory, you might use the FWHM as your correlation width and using the deconvolution factor to calculate a pulse duration. Okay, it could be very short. But in reality, you have no pulse at all. You just have a noise. Okay, so there would be a big mistake if you do not understand, fully understand the theory of intensity autocorrelation. But let's think about why a CW noise will give rise to something like this. 为什么？为什么一个 noise signal 还会得到一个长得蛮像 pulse 一样的 autocorrelation function? So forget about the mathematics. Just think about the definition. What is intensity autocorrelation? You have I of t, and then you shift it by amount of tau overlap integral. That is intensity autocorrelation. Now you have CW noise. So your I of t is a noise. And then shifted by amount of tau overlap integral. What happens? When delay is 0, the two noises are overlapped perfectly, so your overlap integral is still large, right? That's why you have a peak value here. But when your delay is large enough, the two noise waveforms will be of no correlation at all because they are essentially random, right? Then the overlap integral will be close to some constant background. Okay? That's why you have a background here. So now you should be able to explain the meaning of the width of this spike. What is the meaning? Right. 对一个 noise 来说，它的 coherence time 有多长，就记录在这个 width 里面。这个 coherence 根本就不是什么 pulse width， 只是说你的 noise 不是有很快的起伏吗？平均来说，每一次的起伏宽度大概是 coherence time。这个宽度只告诉你 coherence time， 它没有告诉你任何 pulse width 的 information。OK？ And what is coherence time in the frequency domain? Bandwidth, right? So this measurement only tells you bandwidth. If you have a very broad bandwidth, but it's noise waveform, you will have a very sharp and narrow noise spike in your autocorrelation measurement. But it's nothing about pulse width. Okay? In the third example, you may have noise burst. What is noise burst? You have a normal pulse, A0 of t, but you have noise component as well. Sum them up together. So basically, it could be a broad Gaussian pulse as your pedestal, and the noise atop the pedestal. 所以就是一个 maybe 像一个高斯的形状，但是它不是 smooth， 上面有很多 noise 的东西。因为第二项，这个叫做 noise burst。Then what is the corresponding intensity autocorrelation function of the noise burst? Okay. Like this. You have a pedestal. Its width could tell you the width of A0t, the pulse component. But on top of that, you have also a noise spike similar to case 2. So the width is nothing about the pulse, but the coherence time of the noise component. So you have two widths in this autocorrelation function. One is the coherence time of the noise component. The other is the pulse duration of the pulse component. Okay. So you have to be very careful. After the experiment, you have to watch the shape of your intensity autocorrelation function. If either this or this happen, you have to be extremely careful, because that does not mean you have a very short pulse. It could imply you have some trouble in your laser source. It only produces either CW noise or noise burst. So you have to correct your laser source. Good question. 我们的 model 应该是有的。如果你是用我们标准的模型，你会看到呢，是有 background， 它没有掉到0，只是我这个绿色的 curve 是从这里做了 data processing 拿出来，它没有背景值。它没有背景值的原因就是我在第2步的时候，我把那个 delta 给砍掉了。delta 来自那个 constant。那我那边画的就是你做一样的步骤，你每次都把这个 delta 砍掉，再拿来比，那个时候就没有背景值。 但是如果你是 coherence noise，你是 CW noise， 即使你去砍它，你还是有。好，我们想想看哈，从这个东西出发做了假设你用它来算你的 G2 函数。所谓 G2 函数的意思就是我要做 low pass filtering， 而且我砍掉 delta， 我最后才会得到 G2 函数。好，那你就是把这一个东西取绝对值平方，你就得到 I of t， 然后拿它去做 autocorrelation， 你会得到这个东西。那它为什么会有 background？ 你取绝对值平方之后，你一定会得到 positive function， 你不会有 negative， 对不对？那你去做 overlap integral， 两个都是 positive 的 function， 做 overlap integral 不可能给你负值，最小就是想想看0，但是它不会0你要变成0，就是 roughly 你要一半正一半负，才会给你0嘛。要不然就是 OK， 应该这样讲。这里为什么会0？因为当你两个 pose 完全分开了，重叠的部位就是0对0，乘积是0，积分也会是0。但是 CW noise 它在时间上是一直延伸下去的，它不会像一个 pose 最后会掉到0，它只是很乱，但是它永远有。所以不论你 delay 怎么大，这两个不会完全分开。
那第三张不是
第三章其实很像第一章，只是它在那一个Gaussian之上还有一些 noise 的成分，所以 delay 够大，它还是会0对0。What is noise burst? This is your pulse. Noise burst means like this. So when delay is large enough, okay, their overlap is still 0.
其他地方不会有 noise，
就没有了，对，其他地方就没有，这个叫做 noise burst。OK， 好，所以这个的确要小心，这是好问题啊。为什么它不消失？因为 CW noise 本来就永远不消失 ，always 有 overlap， 只是 correlation 不见了。所以 delay 怎么改，它的 correlation value 也不会改变，它就是一个 background 在那里。
那个2比1是举例吗？还是就是
？If it is Gaussian noise, it should be 2 to 1. I don't know what's the case when your random variable is other than the Gaussian. I don't know the ratio, but if it is Gaussian, it's 2 to 1.
Noise burst 那边，它的那个 single pulse 的顶端，就是为什么？就是你在画 single pulse 的时候，是它的 peak 在2，然后 noise burst 那边，它的是因为有 noise spike， 所以它才会长到2。为什么？就是它看起来像是就是一个高 T 的 pulse 加上一个 noise spike 造成右边的 noise burst。为什么就是那个高 T 的顶端跟谁一样？
你说这个为什么不是直接把它加上它？OK， 我们可以这样想哈。我要做第三个 case 是 field 是这两个加，那这一个去做 autocorrelation 得到它，这个去做 autocorrelation 得到它。但是你一起做 autocorrelation 不是只是两个加起来，因为你要做 autocorrelation， 你要先取 absolute square。也就是说 ，in case 3是两个相加后取 absolute square， 再去做 autocorrelation。那你个别呢，就是个别取 absolute square 以后个别去做 autocorrelation， 这两个应该不一样嘛？
所以下面就是做 autocorrelation 后。
Right。第三个 case， 你必须两个复数相加后一起取绝对值平方才去 autocorrelation。它跟各自取绝对值平方做 autocorrelation， 再加起来不一样。Okay, any other question? Wow. Let me finish this slide. Okay. Non-collinear configuration. Previously, we introduced a setup that the two pulse replicas propagate together. That's collinear geometry. But sometimes you can do differently. Say with a slightly different geometry, the two pulse replicas can propagate in parallel with each other, but not along the same axis. Then, after using a lens, they can focus into a thin crystal for second harmonic generation. That is non-collinear configuration. And what happens if you do this way? You will have three output pulses, second harmonic pulses. Number 1 is here, number 2 is here. But number 1 and number 2 simply mean individual square. That means, for example, number 1 is the second harmonic generation of this single pulse. Number 2 is the second harmonic generation of the other single pulse. So mathematically, A1 is the square of the second pulse, which is the delay pulse. A2 is the square of the first pulse, which is A of t only, individual square. But you can have the third pulse propagating in the middle, along the middle direction. And mathematically, the field is the product of the first pulse and the second pulse. Okay. And it simply means A plus B parenthesis square is equal to A square, B square, and 2 times A times B. These three components are spatially separated under non-collinear geometry, but they are mixed with each other in the collinear geometry as we introduced before. And if you use an iris to block the first two pulses, only pass through the third pulse, so you have this one, right? Your second harmonic field is proportional to this one. Then you are using a slow point detector. Your autocorrelation trace is directly proportional to G2 only. So this time you do not need any data processing, no Fourier transform analysis. Your raw data is directly G2 function. So to some extent it's advantageous. Okay? 你就透过这个空间上的区分，直接捕捉了这个你要的 intensity autocorrelation function。那还有好处嘛？既然只有它，你有没有 fringe？ In the collinear geometry, your raw data trace has dense fringes. You need very small delay step to record them. But here you don't need, right? Your delay increment can be big enough, so it takes shorter time to get the trace. And you can save the data processing time as well. So there are some advantages here.